Welcome back, ladies and gentlemen. We are hoping to help each other once again, and you being back is another vote of confidence. I don't want to spend too much time on the niceties, because today is gonna be one long session, and it's gonna be, brace yourselves, it's gonna be one long session. Remember to like if you like, and then hopefully you wouldn't be here if you didn't like. And then also please do subscribe, because when you drop, you have to be the first to know. Now let's deal with our very long session today. We are going to be looking at what, at our, previously we looked at the weighted resistor model. All right, the weighted resistor model is basically, we might not have called it that, but this weighted resistor one, as we see, each resistor with this value, there's a 2.5 there. It is basically going to be, you saw how when we were analyzing this, how that was the 8 bit. All right, like the 25k there being the what, being the 4 bit. So this is more like each resistor has a what, has a binary weight attached to it. Now, so the weighted resistor model, unfortunately, like every other thing, will have its own pros, advantages, merits, whatever you choose to call it. All right, so those will be, for instance, the principle. You saw how this was easy to work with. This was such a, today you're gonna say, wow, there's nightmares out there. So this is the problem is, okay, not the problem here. The good thing about this is that it's very easy to analyze. I mean, it's so straightforward. As you could see, it was basically dividing into I think we were dividing each resistor value to get a current, and then the current was simply what, working out into a voltage. The analysis was so straightforward. So now the principle of operation is quite simple. But then also, I think that you have to know about this. The what call this, the conversion rate is much it's actually very good. Now we will look at the cons as well. The cons, demerits, the disadvantages, whatever else, nightmares, whatever else you wanna call it, the horrible aspects. So this is the cons, the disadvantages, and look at just that one scenario. We only have 4 bits there. Let's suppose we wanted to have 5 bits. We would have to have another resistor there. It will be higher order. Therefore, it will be around what, 6 comma something there, to be 6.25, I think. Now, the values. Where are you going to get all these values? I mean, really, honestly, if obviously the values go off, it will affect the current. So where are you going to get all these values? The range can really get worrisome. It can be too much. Also, uh, when there's deviations, when the values are not accurate, when there's deviations, when something goes wrong, and each result that gives you something wrong, this error in totality is going to accumulate, and it's going to each error is adding up to the next error, is adding up to the next error. So you cannot afford any errors in this instance here. All right. Also, these resistors, if you look at them, I already alluded to if we wanted an A16 there, if we wanted to add an A16 there, an extra bit there, A16, we would have to have a value that is half of this. Besides it being a challenge on its own to get that value, uh, look at how small the values are getting. So what are you doing here? The currents are becoming more and more and more. So this thing is having a situation where your currents on each lane are actually what, your currents are different, and therefore the MSPs require much larger currents than the other resistors. And now, if you go obviously with those currents there, what they're gonna get, heat is gonna be generated, and obviously there's going to be power losses as well there. So now, looking at these multiple resistors, it will obviously be a tremendous challenge to actually match impedances here. Remember, impedance matching is a must. It's not otherwise. What happens with the energy? There's reflections in the energy, and then obviously there's what, there's greater losses. So you need to have your what, impedance matching. Now with so many resistors, that simply says we are going to have a horrendous challenge. Now, the bigger resistors tend to what, they tend to give you greater errors. The bigger the resistor, the greater the margin of error. So all these challenges here are what you might encounter with the what, with uh, 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 your weighted resistor model. All right. So what's the alternative to this? We then go for the next one that we look at, the R-to-2R model. All right, what is this model here? If I can move this quickly just to show people, let's just go up a little bit and say, what are the advantages of this new model here? There is only two resistors. If you look at that circuit there, there's only two values, R being one value, 2R being the other value. There's only two values here. All right, so we don't have that horrendous challenge of what, of a nightmarish range. All right, also there's no need for precision here. There's lesser need for precision in with this situation here, right? And then obviously it is obviously going to be much cheaper. And what? Why? Because precision comes with cost. All right, precision comes with cost. Now, if I'm going to say, all right, what are the disadvantages? The disadvantages of this is conversion rate is a little bit slower. If you see how long this circuit is, and it can get longer. Remember, this is just 4 bits. We could have had another bit. So all those currents flowing all the way there, that the conversion rate is much slower. All right. And now we're gonna go and prove it when we say analysis is a nightmare here. Analysis is a nightmare here. I'm gonna give you a throwback to the superposition method. You're gonna look at the throwback to the Thevenin method. You're gonna also worry about your basic Ohm's law, and it's gonna be a nightmare. You will see. Let's go ahead and anyway, this is the R-to-2R model. So all you have is the two R's there, and then you have your R's there, and then now we are going to go ahead and try to analyze how this works. We've seen how the other one works. Now we look at how this model works. I will want to say, let me start by, I will deal with this one by one. That's why I brought the concept of what? Of superposition. I will want to see what A contributes in our circuit, what B contributes individually, what C contributes. Because to try and do it all at once, that won't happen. So what we'll do is we'll only supply with A, analyze the circuit, and say, okay, A is going to give, or what we're going to do basically is we're going to start by Thevenizing the circuit. All right, to analyze this, I'm going to need to Thevenize the circuit. So what I'll do is, let me first see if I can ungroup this. Okay, now I can ungroup it. What I'll do now is I will remember to Thevenize. I'll disconnect this guy. Right, I'll disconnect this guy. I'll only put it back when I'm done. What I want to know is, what is A, B, C, D when they have power? What would they contribute at this point, at this output here? All right, so what we're going to do is I'm going to name each of these outputs. I'm going to name them. Now I'm going to start with A, so I'm just going to say A for that point there, just to say it corresponds to A. That vertex there corresponds to A. So now we're going to try to analyze what A would contribute at that point. So what A contributes to this point here, the point of supply to the op-amp, or to the output rather, what A contributes plus what B contributes plus what C contributes plus D, what they contribute individually. Hence the concept of what? Of superposition. They are going to superimpose, they are going to send their own individual currents to that point there. So we want to analyze what they will contribute as individuals. Then we can say, okay, together this is what they are going to give us. Now let's check A. Let's say we have, now the nightmare begins. Let's say we close that circuit there to 5 volts, all right, and leave the rest of them to ground. So what we are doing here is, remember superposition, we deal with the one source, we deal with the other source, we deal with the other source, we deal with the other sources, and then we see how these sources contribute to a specific point together. So we're going to say, now we're going to say, with what does A contribute? I'm going to say, there is my A. What does my A contribute to point A? All right. Is it difficult? No. Everything else here is grounded. If I ground, let's first remember basics here. If we have two resistors, let's call this resistor R. Let's say the two resistors are equal, so they both have the value R. Now, if you are going to want to put them in what? In parallel, what then happens that the total is going to be the product over the sum. All right, over the sum. This is when two resistors are put in what? In parallel, and they are what? And they are equal. What will then happen is that you're going to have R squared there over 2R at the bottom, which means basically R over 2. The whole idea here is we need to know that if we put two resistors in what? in parallel and they are equal, you are going to get half the resistor size. Now we go and apply this here. We say if these ones are on ground, the two of them on ground, so these two are parallel. So I'm going to take a different color to highlight this. So these two are parallel here. They are both on ground, so they are parallel. They are connected to ground on one side and connected together on the other side. So they are connected on either side, so they are parallel. So if they are parallel, both of them are 2R. What happens is 2R being the one value, I hope that color can be seen, by 2R. Well, we have already said 2R plus 2R. I want to prove this. This is going to be 4R squared over 4R. So therefore, you can see the 4s will fall away. Now what I do here, 2R by 2R over 2R plus 2R. So this will be 4R squared over, yeah, so that is fine. So what you see here is that the R will cancel that and we have 1R left. What is that? It is half of each of the resistors. So what we have here, we have a resistor R left there. All right. So now, what then happens is this R here is now going to be in series with the other R. Okay, so they give us 2R again. So now, if they are in series now with the other R, I'll change the color just for clarity. I'll take a different color. Now, if these two are now in parallel, they're in series, so they become 2R. But they are connected to ground, so the other one now is parallel to them also, and it's connected to ground, which gives us back that scenario there. So what do they do? These ones here, these 2R and these 2R give us the other R. Again, that happens again. I think you can see the pattern now. What that happens, let me get a different color just for clarity. Let me take this blue one. Now, that R now, remember that was absorbed into R. That 2R was in parallel with this, so it gave us this R of green. This is the overall. Up to this point, this is the total. Now, we have got a new total here, which is 2R. Now, this 2R is parallel to this 2R. So what happens is that this whole set here, this whole set has just been giving us what? It's going to be 2R now. It's going to be replaced by one value. I'll put it in red. So this whole set here, up to this point here, that whole resistance there is reduced to what? To where am I? Let me first make sure this is R. All right, this is 2R. Then 2R parallel to 2R gives us that R there, and that R is in series with this. So ultimately, we have only these two values here. Let's hope you understood this. What did we do? We started off with these two. They were in parallel, so half, because they're equal, half is R. One is 2R, so half of it is R. So that R is the total. So at this point here, which was the yellow, we had an R. That R is connected to ground on one side and connected to the other R. So together they give us 2R. Now that 2R there, and it's parallel to that 2R, therefore it gives us this R here. So that point there was another R. Alright, so that R and this R give us 2R with the blue there. Now this 2R here is what is parallel to these 2R. Again, half of 2R, which is R there. So ultimately, this whole set here, I will encircle it in red. This whole set actually just worked out to what? To have one value, which is R. So what does it mean? It looks like in this situation here, we have, I'll redraw this circuit just for clarity. We have the 5-volt supply. All right, that 5-volt supply. Okay, what is it doing? It is going through 2R. Okay, and then going through point A. I hope you take your time to notice this. Going through point A, there is point A connected in between, but then we've got that 2R there. That all R, the equivalent of the rest of the circuit with this arm, which is another 2R. So, I didn't indicate that this is 2R. It is this 2R from the 5-volt, from the 5-volt there, and then we've got the 2R that was the overall analysis of the circuit. So I hope this is clear. That's why I said it's a nightmare. You need to have your basics in tune here. You need to have your basics on song. Otherwise, you're gonna have serious discord. Ne? So now let's say this is now easy. After we see how this reduces to a simple resistor, all of this, because of being connected in parallel, reduces to a simple resistor, which is just a what? 1R. And that 1R is in series with this R, and we've got 2R here. Let me probably put this 2R here. That is the 2R that we have here, connected to. It is the equivalent of the whole circuit from R up to there, because they were all parallel. So they kept reducing until they were what? They were just 2R. So now it looks like we have a very simple circuit. Ultimately, we have a very simple circuit. So as far as we are concerned now, VA, I'll call it V at point A. Okay, and this is due to the A. This is produced by A. Okay, at point A, VA, because of the A source, all right, is simply this. So what do you have? You have two resistors in what? In series. So you are taking the voltage between them and they are equal. Therefore, your output there is equal to these two are at the bottom connected to ground over the total, which is the whole from source to ground, which is 2R plus 2R. What am I doing? All right, times the supply. Okay, this is what times. All I'm doing is saying R over R total. Okay, but our R is, this is confusing, eh? Our resistance, let me not say R because they already have a value of R. Let's say our resistance, our resistance that we're measuring across, which is that one there, over the total, which is the two of them together, times the supply. That is our usual formula, and that will give us obviously 2,5 volts. All you've done here is analyze the one source, just A. You've only looked at A. So A gives us what? Gives us what call this 2,5 volts at that point. Are we done? No. Hell no. So we go on to the next analysis. So we know this one contributes 2,5. So all right, here this contributes 2,5. All right. So now let's go and see what source B. So what we'll do is this one goes back to ground, but we close source B. We said we are going to treat them individually to see what they contributed at that point A. We must remember that, I must ungroup this. I think it's grouped. And then I think it's now okay. What I then do is pull it apart because we're analyzing without the supply. Okay, so what is this contributing? What is it gonna give to our what? To our circuit. So I'm doing superposition here. I've dealt with source A, now I'm gonna deal with source B. I'm gonna deal with source B. I have a B will do this. All right. So what will do B do? It means everything else here is on ground. Everything else is on ground. So what do we do? Do you realize that it is actually going to be easier? Let me redraw this. Let me move this to a safe. I know it's gonna give me nightmare to move that side. Oh God, where did you go? Wait, I clearly hope. All right, let's leave it for now. I don't need it for now. So I hope it didn't jump into another page, but we'll see when you get there. For now, let's leave it. We don't need it anyway. So in fact, I need the space. It's fine. I need the space. We know it's there. Now, what is happening here is simple. We are now going to analyze B. We want to know what B is going to contribute. I'm going to write it when I'm done here. What is going to contribute there? All right. So it's easier for me to redraw this. It's a nightmare. It takes forever, but I have to do it. So what I'll do is I'll redraw this circuit so it's clearer. Why am I redrawing? To make it clearer. So I'm going to put mine. In fact, no. This is not grade school. All right, let's just take all of it as it is. Our job is not to draw things here, né? So we're not going to spend time on the drawing here. What I'll do is I'll do this. I just want this circuit here, but let me make this one smaller because it's just reference. Yeah, what again? I've got more space on the one that I'm going to work with. Now, all I want to do here is this. I want to change my diagram. I want to put my let me first do this. Oh, what did I do? I don't understand. Yeah, all right. Now I want to ungroup this first. Looks like it's a nightmare to work from that corner. All right. So what I want to do, I want to move this guy. I'm gonna move it up like this. I'm gonna draw it with a red pen up there. I'm only doing this to so that it's hopefully it's gonna make it as easier to see. What I'm doing is gonna be, I hope it's going to be easier to see. So all I'm doing is connecting that there. There is my 5 volts. All I'm doing is, so people don't think I'm being funny. I'm not gonna remove it. I'm just gonna. Why is it not? Yeah, all right. It's still there, but I want to put it at the top so that people can see what I'm talking about. What you can then see here is the rest of these circuits here are what? Are parallel now. So what do we do? If you come and you say, I want the voltage there, I want to know, this is still going to do the same thing. That analysis here is going to be, let me go back to my yellow. No, it's not clear enough. Let me go and take this one. These two together are going to resolve to an R. We've explained why. So these two are going to be 2R. They're going to resolve with this. Let me take a different color. Just to, so people can, maybe it can stick. Maybe people can see what I'm doing. So when we resolve this, this is now 2R. This resolve to an R. This is going to be 2R. So this and that is parallel. So this is going to resolve again into an R. What do I have now? So this set here, this is 2R now. This 2R is connected to ground. So I've got 2R here and I've got 3R on the other side. So the two of them are what? The two of them are parallel because they are both connected to ground. This one, that of the voltage, I put it up. So I'm going to work parallel. These two are now giving me a situation like this. Let me redraw. These two are now giving me the black R on there and the blue R there, and they're giving me 2R. They're each R, so these are giving me 2R. So what I might as well do, I might as well put 1 2R. I hope people get that. Okay, this is my 2R, combining those two, and this grounded because they were all parallel to ground. They were all parallel and connected to ground. Now then, at that point then, they are connected to the 5 volt through the R, through the 2R. This is 2R. Remember, all I did was move this up there, just to, so people can see what I'm talking about. So people can see that coming here, this is now parallel to that there because they are both going to ground. So if people can get that, what do we have? We've got this R. Oh, by the way, this is 2R and the 5 volts. Okay, so these are and that 2R are still in their position. I just read through so that maybe it's clearer what I'm doing. So there we have our point A. All right, so all we need to do now is work out this resistance and that there. What is it going to be? This is going to be 3R. 3R, R plus R is 3R. Sorry, R plus 2R is 3R, parallel to 2R. Okay, and this gives us 3R times 2R over 3R plus 2R, and that gives us 6R squared over 5R. That will be 6R over 5. The squared and the R, they resolve each other. Now this is what we get. This is the resistance, but this here, if I redraw, this is the equivalent of this parallel network here. All right, this is 3R, which is this leg here, parallel to that leg there. But we still have 5 volts through 2R through the parallel leg. So what we have here, we want the parallel voltage. We want the voltage here, the V parallel. Okay, why would we work out V parallel? It's easy. What is total resistance? Therefore, R total is simply equal to this 2R plus the parallel. Let me call this R parallel. Right, V parallel is R parallel is those sets. Let's call this R parallel, which was that. So plus R parallel, which is equal to 2R plus 6R over 5. I prefer to leave it like this because it's gonna work itself out. You can get commas and whatever, but it's gonna work itself out. So I'll leave it like this. So this is going to be, as fractions. So this is going to be 10R for this. If I make common denominator, it's going to be 10R. 10R plus 6R, it's going to be 16R over 5. This is our total. All right. Now we want to work out the the voltage here. So we must first get V parallel. All right. Let me move this a little, maybe just a little to the left, so that this one can follow and give me a little bit. I'm trying to get a little bit more space because I can see I'm going to have a space problem here. Now, when we have that, what we can do, we can then work out our, let me take a different color so that people, there's no clashes here. Our V parallel, now we're going to work out our V parallel, which is the voltage at that point there. Our voltage at that point is simply R parallel over R total times the voltage supplied 5 volts. Therefore, it's R parallel over R total times 10 volts, times the supply, which is 5 volts. That is going to be R parallel is 16, R over 5, divided by R total. Oh, no, this is R total. I just put in R total then. So we need R parallel, which is 6R over 5. This divided by R total, which is 16R over 5. But this is times the voltage of 5. Alright, so 5 into 5 falls away. R into R falls away. What do we have there? We have a common factor of 2, which leaves us with 3. A common factor of 2 makes that 8. Alright, so this becomes 15 over 8. What is 15 over 8? I believe I might have made a mistake somewhere, but let's continue. 8 there is going to be equal to 2. It shouldn't be 15, it should be 16. I've lost something here, but let's see how I lost it. 2 remain. Okay, let's go on and say no. Let me just leave this as it is. Let me leave as it is. Why? This is not my final step. I don't want to do too much calculation before I get to my final step. Let me leave this as it is. It has given me 5 into 5. 2 there gives us 3. The r's cancel. So this gives us 15 over 8. Let's leave that as it is. Why? Now I'm going to go and work out my voltage there. My voltage there is V at point A, as contributed by the B source, is simply going to be these two. Let's come in. Once we've got a voltage parallel there, once we've got a voltage parallel here, right, that voltage is going to be shared by these two resistors, right? So I'm going to have 2R over 3R, 2R over 3R times the voltage parallel there, which is 15 over 8. Okay, there the R's fall out. Alright, then 3 goes into 15. How many times? That's 5 times. And 2 goes into 2 one time, and into 8 4 times. And if you look at this now, 4 into 5 is going to be 1 comma, into 10 that's 2, and then into 20 that's 5. So it's now right at the end. It's a little bit of a nightmare to write it. Now this is the voltage. What do you see? This is what that source contributes. 1 comma 2 5. What do you see already? factor of 2. This is 2 times that. This is half of that. Already, that shows you. You can already predict that this is going to be half of this. If we are good for the next exercise, then it's going to be what? Half of that. But let's go ahead and see it. So I don't know if you analyze this. We first resolved this. This was my first step. We got the R there. Okay. The second step is these R's become what call this? Since they're in series, they become 2R and they're now parallel to that. So this resolves to 2R parallel to 2R, which is another R. Alright. Now we've got 2R, and then this 2R unfortunately is going to ground there, and it's branching there. This other pair is going to ground. So this set and that set are parallel. So 2R is parallel to 3R. But we want the voltage there, hence the step. So we started here by what? By showing what this reduced to 2R parallel to 3R, which is that. Then we got we used that to calculate our what? Our R parallel, and we got the value. We didn't really need the value, so we didn't really resolve the fractions. We just left them as they are because they clean themselves out. So you don't have to worry about them. They will clean themselves out. Now, then when we're done with that, we remember that okay, R parallel we still need to know the total resistance. Hence, we did the total resistance here. Now, after doing the total resistance, we can work out the voltage. Well, there are different ways. Remember, there are different ways. We can use voltage divider or current divider. So we've done that before. So you can use whatever you're comfortable with. Right now, I'm trying to show how the analysis works. How this analysis. I'm sure right now people are thinking, what? Some people may be thinking, what? But anyway, it's not what time yet. We are still going to be fighting with this. We're not done yet. So now, after getting the parallel, the voltage parallel, now it is shared by these two. That's all we did here. You said R parallel over R total. We got V parallel. That is that. Then we came here and we shared. We said 2R over 3R because R and 2R is going to be 3R, which is what we did here. We multiplied by the voltage we got there, and we got our answer there. So I was running through it again. I'm probably moving a little bit fast. I don't know. It's because I have a lot of work to do, and this is going to be an extremely long video. Otherwise, slow it down, go at your pace, slow it down. With these days, we've got the benefit of changing the speed of a video. If you feel that probably it's a little bit too fast, you can downsize the what call this the speed, the pace a little, and probably you can play it as many times until you get what you're missing, or you can ask questions and we can come back to you. All right, so this is the advantage again of subscribing. All right, now let's go and say we are not done. We've just done these two. We still have two more to do. We still have bigger nightmares. These were simpler sketches. This was the simplest. The first one was the simplest. That's a little bit trickier. You can bet that the next one is going to be even trickier. So what do we go and do? We go and say, let's look at the next one. So what do we have here? We've got 2,5 here. We've got 1,25 here. And this dude is too big for my liking. I have seen that I'm struggling for space here. So I'm going to try to move it a little bit and reduce the size. Now I'm going to try to ungroup it. Ungroup, because we are thermonizing here. We are thermonizing this circuit. So we want to remove the load resistance. This is our. Want to work out the voltage at a certain point. So we remove the load. It's supplying the op amp. So I want to remove. It's taking me a while to remove this. And it's already not helping with the time. I know I don't have. I'm going to remove this really. I'm really going to remove this because if I put it somewhere, well, last time it disappeared and another time it will probably cause us other problems. So we will know it's there. We'll come back to it. So now when you are done, we go to the next one. So we are going to work out VC. I would like to have black to start with, VC. And we have to analyze VC first. How do you analyze VC? It means, therefore, this time around we close that one there because we are supplying with VC and the rest of them are grounded. It's easy. These ones here are going to what? Are going to resolve. And those ones there are going to resolve. Let's see how that happens. These two, I'll do it right there because doing this sketchy size does not make sense to me now anymore. We know the circuit now. So these two are going to resolve obviously to, because of being parallel and they're grounded on the one side and they're connected together on the other side, so they are parallel. So 2R times 2R over 2R plus 2R will give us, again, you saw half of it, half of each, because they are equal. So that is R. So these two, this one side is 2R. All right, we are done with that. It's connected to ground. So what do I have? I've got my one side being 2R and connected to ground. This is when I resolve these ones here. Simply by what? By working out the parallel resistance between this pair here. Gives me R, and then you work out the series resistance with those two, and they give you 2R back. But we can't connect it there because this is now our source. So it's not parallel. So this is 5 volts. This is this part here. Okay, through 2R. This is 2R. And it's connected to that one there. It's connected to that one there. So they connect there. But there is where the others come in. These ones, what do they do? These two are in series. Okay. Remember, we're working out for point A. These two are in series. So if these two are in series, they're going to give us an R series of what? R series, let's call it R series 1 because I don't know how many we're going to have. R series 1 is going to be R plus 2R, this pair here. All right. That pair gives us a simple 3R. I don't know. That was not difficult. Let's go. You can see that this is also grounded, so that this pair is grounded, that pair is grounded, so they're going to give us a parallel network here. Let's work out the parallel value. P1, because we don't know if we have another set that we're going to work out. So it is 2R. They are connected to ground, and they are obviously in parallel. All right. If they are both connected to ground, it means they are connected on the one side. Then they are connected, you can see they're connected on the other side. So they are this set and that set. This one goes on the set and that set are actually in what? Actually parallel. So let's work out that parallel value is 2R parallel to 3R. We've done this before, and that gave us 2 times that is going to be 6R squared. R squared over 2R plus 3R is 5R. Now R into R squared is R, so you are going to have 6R over 5. We've done this before. All right. All right. So now we have a value here. What is that value? It is the value of the parallel network up to there. All right. We still have, they join only here. They join with 2R and the 2R from the source here. This join, that join, this join here is that join there. So this parallel network must add up to R first before the join. So we've got an R series 2. And that R series 2 is what? Is R parallel 1, that set parallel to this and that parallel. And then they join to that. So it's R series 2 is R. That R. And then in series with this parallel set here, which is R parallel 1. And it is easy because it is an R plus 6R over 5. This can be 5R to make it one common denominator. This can be over 5 as well. So that makes this 5R to make it over 5. 5 over 5 is 1, so we haven't done anything wrong. So this is 5R, that's 6R, that's 11R over 5. Okay, I've resolved the 5s together because this would have been 5 over 5R. So if both of them are over 5, we can add them. And then that will be 5R plus 6R is 11R over 5. That is straightforward. Now, but this is the one that is parallel here. This is the R series 2. It is parallel to our what? To our 2R, to that 2R there, because they are parallel. On the one side there's ground, on the other side there's ground. They are connected, so they are connected on ground, and they are connecting this side, so they are parallel, but they are connected to the 2R, which goes to the 5 volts. So this is our situation. Now, what we want is the voltage here. The voltage here at this point here. How do we do that? We've got the total, what did you get here? We got R series 2. We did not get R total. We haven't done R total yet. We haven't done R total yet. What did we do? It's R. So we did this set here. Okay. Plus R parallel 1. We did this set here. After doing this set here, we have to do R parallel. So R parallel, which I'll call R parallel 2 now, is for this set here. It is going to be equal to 2R parallel 2 R series 2. It's getting long. That's why I said it's a nightmare. Now this is 2R times R series 2 is 11R. Okay. Over, oh, no, not 11R. 11R over 5. Okay. All over 2R. Remember, is product over sum plus 11R over 5. This is going to be, this is a simple multiplication there is 22R squared over 5 divide by this one here. We have to get a common denominator, this which is 5. 5 will make that 10. If I make it over 5, so it's going to be 10. This is 10R plus 11R, which is 21R over 5. Okay, all I did was get a common denominator there and add it together. If you don't see it immediately, do it on the side, do it for yourself. It's simply common denominator. This is over 1. This is the same as over 1. So once I make it, once I change this to 5, I must multiply that by 5 as well. That gives us 10R. 10R plus 11R is 21R over, but this is changed to 5, so over 5 altogether. So it's a fraction divided by another fraction over the same denominator. The denominators cancel because it's like they swap around. And what if this fraction was to be turned over, and then the 5 will be on top and it will cancel that 5. So I think that is not a problem for people who have their basics. Unfortunately, we are trying to do engineering, but our mathematical basics are also of keen interest. We must know them. So at the end of the day, what do we have? We have a resistance of 22R over 21. This is just a parallel. This is a nightmare. I said before, when you started off, this is a nightmare. Now all we have is the parallel resistance there. We still need to add 2R. So our R total, the journey has been going to R total. Is there an easier way to resolve it? Probably you could go with the current divider network and it will be easier. But for me, the current divider is going to be a nightmare because you have to, how do you get the current in the first place? How do you get the current in the first place? Because you're going to have to what? You're going to have to, you could say, even, no. In fact, you see, even though there are many ways to kill a kidney, some ways are smarter than others. Well, again, some ways are more human than others. So there are some ways are evil, you know. So there's different ways we might approach questions, but some approaches are not exactly clever. All right. I believe that each instance has an easier way to look at it. Okay. So now I believe that what I'm doing might not, maybe in your opinion, be the best way, but it works. It works. Let's go on and say we want R total. So all you need to do now is add, this is R parallel here at that juncture. I shouldn't make it look that way. I should make it look at the junction, there. So this should be, R parallel is actually measuring these two parallel networks there. This is what we call the R parallel 2. So this R parallel 2 is looking there. All right. So now what then do we have? What then do we do? We then go on and say R total is that resistance plus R parallel 2. So it's 2R resistance from the source 5 and R parallel 2 plus R parallel 2, which is equal to 2R. This is the value plus R parallel 2 is given as 22R over 21. I'm going to give it a common denominator, and this is going to be over 21 there. Will make this 21 times more. This will be 42R. 42R over 21 plus 22R over 21. Maybe I should have been taking these steps like this. Maybe it would have made life easier for people. So then this here would have been 64R. 64R over 21. I don't want to make it is the let me see, 64R over 21. Is there really a need? Could I divide that by 3? Yes, I can, because 3 can go there. No, 3 can't go in there. 3 can't go in there. 7 can't go in there. So no, I'll leave it as it is. All right, I will not want any fractions or any commas and whatever, any radix points. All right. So what I'll then do is I'll leave it as it is, because 3 is not a common factor here. I don't want to hunt for common factors now. Just leave it as it is. I only see 3 and 7 here. And then 3 and 7 cannot go into 64. So I'll leave it as it is. Anyway, let's go and say, but we want the voltage at that point. So what we want? We want all this was for us to be able to work V parallel. That point there. What is this point here? This point here is that point there. We want the voltage at that point. Okay. What we are looking for now is V parallel. Okay, at that point there. So what are we going to do? Let me probably call it V parallel 1. Because I'm seeing myself needing a V parallel 2 here. Let's call it V parallel 1. Alright. So what we're going to do is we're going to say V parallel is simply going to be R parallel 2 over R total times V supply, which is 5. Now that is going to be what? That is going to be, this guy is the total. R parallel 2 is there. This is R parallel 2. Let me underline these things so I can easily pick them up. R parallel 2 is 22R over 21 divided by the total 64R over 21, and this is times 5. Alright, so 21 is common for both of the what is a denominator for both the what? The numerator and denominator. Remember, our numerator is a fraction and our denominator is a fraction, and the 21 is common as a denominator for both, so it falls out. Now, this here can now be resolved to 11. The R falls away, R over R. This here can, all I did was divide by 2. There is 11. Divide by 2 there, that's 32. And I will leave my voltage there as 11 times 5 is 55 over 32. Okay, so I will leave it as it is. I will not try to struggle with it. I will leave it as it is. When I connect the other fractions, are going to make it simpler. I'm going to just do the final calculation. So now we go and say that gives us this voltage that we get here, gives us the voltage across 2R, and it gives us the voltage across the other network, this other network here. Okay, the voltage V parallel 1 is the voltage across this. We don't need that, leave it. But it's also the voltage across the other network. So I don't want that. I want V parallel 2. I want this voltage here, V parallel 2. Now, to get V parallel 2, I must get the other parallel there that we call R parallel 1. Alright, this R parallel 1 over the total resistance there, which was R series 2, that one, times that voltage is going to give us that. So we've got this R parallel over the total times the voltage will give us V parallel 2. Let's do it. V parallel 2 is equal to, now I don't know, taking this long to get here, I don't know if it's still wise for me to go on and do the final one, because it's going to be very long. It's going to be very long. Probably I will leave it at, once we see that the trend is working, I don't know whether it will be induction. I will use the term induction correctly, or whether it will be proof by induction correctly. But you will see that the trend is working towards. If this proves to be half of this, then you can see that we can say, okay, similarly, we can say mathematically, similarly, D can be proven to be. I mean, I don't know. What I'll do is I'll do that just to cut this video and not make it too long. But I will leave it as your homework to do the D. And then if I will come back with the homework, so to divide the section and not make it too long. So that probably you can understand. Because if I pile up too much stuff, that may not be very, very exciting for people right now. It might be a little bit of torture. And I pile it up, the whole video might be a nightmare. So what I'll do is, if we do get half here, which is 0.625, If you get 0.625 here, we can see that the pattern is leading us to that one being half as well. All right, you can see, I mean, we've been dealing with the same, with a very identical set, so you can see that it will be leading us to that being half. If this turns out to be half, this is half of that, this is half of this. If this C tends to be half of B, B is half of A. If C tends to be half of B, then I will simply put a statement that similarly it can be proven that D will be half of what? Will be half of C. But I will leave it as a homework to actually complete the work and do it. If that proves difficult, then I will answer the homework so that we divide up the videos. That's the whole point. Because I'm also feeling tired of this amount of work. Especially, I'm concerned about whether my students are still with me or whether I've lost them somewhere. So now let's go on and say, I don't want to lose you in too long a path. Let's rather cut the paths, all right? So we'll come back and finish the other one as homework. So let's do V parallel 2. V parallel 2 is there. So that is from R parallel 1. So let's do R parallel 1 over, this is R series 2. R parallel 1 plus R. R parallel 1 plus R is R series 2. R series 1 was this one here. So this is R series 2. So R series 2 is given by, okay, let me first give the formula. R series 2 times the V parallel 1 will give us V parallel 2. V parallel 1 will give us V parallel 2. So this here is going to be R parallel 1 is 6R over 5, right? Yes. Divide by a fraction again, R series 2, which is 11R over 5 times the voltage V parallel 1, which is 55 over 32. Okay, now let's see. These two denominators can cancel. The R goes. Now what do we have? We have 11 there going there into what? Into 55 5 times. All right, you've got a 2 here leaving us with 3 here, and you've got a 16 here. Okay, so what we seem to have here is 15 over 16. Are we done? I don't want 2 there is 3, 2 there is 16. V parallel 2 is 15 over 16. Okay, now V parallel 2 is at that point there. That's not the voltage we want. We want the voltage at A. So we must now share V parallel 2. V parallel 2 is across this. So 15 over 16 volts is across this. But 15 over 16 volts is also across those two. So these two can share voltage divider. They can share that V parallel 2 to give us VA. So VA now is in property called VA, specifically from C, okay, is going to be 2R over 2R plus R, which is 3R, times the incoming voltage, which is V parallel 2. V parallel 2 is 15 over 16. And as you can see, this goes there, that goes there 8, this 3 goes there 5 times. And 8 into 5 is 0, comma, into 50 is 6, 50 is 48, 50 minus 48 is 2, so into 20 is 2, and then you're left with 2 times 8 is 16, you're left with 4, into 40 is 5. And yes, it is 0.625. Okay, so we got 1.25. Half of it went to B, 1.2, we got 2.5 for A. For B, we got 1.25, which is half of A. For C, we got 0.625, which is half of B. Similarly, it can be proven. Similarly, it can be proven, it can be shown. We've seen this in textbooks. I'm going to do it. It's shown that D is equal to C over 2, which is equal to 0.3125. So you are supposed to get here 0.3125. But regrettably, this is a very long session to get here. It's been a marathon already. So I suggest that my students go and do this, prove this D on their own. Prove that D is equal to 0.3125. You've seen the pattern. This will prove to you that you cannot, you actually been following us, how we are able to what, to get to these values so that you can do it on your own. All right. So I hope you can go and do it, but then we'll come back, we'll make it our homework. Work out D. Similarly, okay, work out V at point VA, all right, from D, all right. So this is what we want. So what were we doing here? All right, I want to, because this was the tricky part to prove this. So once we've proven that this is basically, as you can see, this is the most significant bit, is giving us the highest voltage. This is the, but the factor here is 2. So this is the 8 position, the most significant. This is the 4 position, this is the 2 position, and this is the 1 position. All right. So we could have used a different source where it could have given us those very values. We could have had a value of 8 here, whatever, but it's not really, that's not really important. We can use that relationship. All we want to show here is the relationship of what? 8, 4, 2, and 1. Now, I do not want to exactly cut the video here. I wanted to cut the lengthy explanation that is very confusing, but let's take a breather and then come and see that you can freeze your video at this point. But where are we going with this? I just wanted to count no, let me not do this. Let me take it back. Let me rather open a new page. Do I have a new page? Yes. This is the page I had. What we have seen, that this is 2.5 volts. Okay. This is 2.5 volts. The A contributes there 2.5. The B contributes what? Half of it, 1.25 volts. The C contributes what? Half of it, which is 0.625. And you would have seen that, yes, similarly it can be proven that this one here would contribute what? 0.3125 volts. Now, but the point here is, all these voltages are going to what? They are going to be sent here. They are going to be the voltages. If you look at current directions here, the source is this side, so the current directions are that way. So as you can see, according to superposition, what's going to happen? These currents are going to add up here. So meaning what? Our voltages are going to add up ultimately. So what do we mean here? We mean that at the end of the day, it's as if we've got a voltage source at this point. This is why we're saying we're Theveninizing. All these are like our Thevenin voltages. All right. So it's like we've got a Thevenin voltage of the sum of these. All right. Remember, it's not going to always be a 5 volt source. If the 5 volt source, if the source changes, you have to change the what? The values are going to change. Obviously, we've been working this from what? From 5 volts. All right. But assuming that this is our voltage, if we sum this up, we are going to see that we have, I'm not going to waste time with this, 2.5 plus, I'm using a calculator here, 2.5 plus 1.25 plus, not a difficult sum, but I don't want to waste time on little errors, 0.625 plus 0.3125. Together, they give us 4,6875. Yeah, not exactly 5, but well, look, if your steps if your voltages can be altered so that it gets as close as possible to 5, if that's what you want. Okay, the steps are also very important. But what I want people to notice here keenly is that this is our what? Our VThevenin. We've been working out our VThevenin. We've used superposition because we've treated each source independently, and we've calculated at what? At a voltage Thevenin, which has been worked out using what? With superposition. Remember, it does not matter how you get voltage Thevenin, as long as any one of the methods can be used to what? To get your VThevenin. All right. So now, It means, therefore, we must know a resistance here. Because with Thevenin, we also need to know the Thevenin resistance. So this here now, that's why we kept removing this. This is where we now come and say, let's put back our what? Our load. And our load is our, in this particular case, is our op-amp. Now we can say connect it back, and you can see that we can amplify this where our feedback resistor, our feedback resistor here can give us whatever value whatever design value we want, all right, what we aspire to. So this here will be grounded, and that there is grounded. So this is basically what we've been trying to work out. So we need to work out R-Thevenin as well. R-Thevenin, how do you work out R-Thevenin? By shorting out the sources, replacing the sources with their equivalent resistances, right? So what do? You short out all the sources, because their equivalent resistance is what? It's like the equivalent resistance. We didn't say they've got. We didn't mention any internal resistors. So resistances. So what do if we did mention as an internal resistance for a source? We treat that source as having what? An internal resistance of 0, meaning that it's like a short. So we short all the sources, meaning that we ground this anyway. So we ground the whole lot. When we ground the whole lot, what do we have? We have these two being in parallel. The whole lot is grounded now. This is how you do This is how you do R-Thevenin, by shorting out the sources. All right. So that is going to be R. But this R and that R is going to give us 2R. These two R parallel to this 2R, that is going to give us another R. I think we see where we're going with this. This is R and 2R, and it's parallel to that 2R, so it's going to give us yet another R. Now, then we've got this R, which is total up to there. Now you've got that there, parallel to that there. So the whole Thevenin resistance is just 1 R. So this whole lot, if it's grounded, if you ground all the inputs, then this whole lot is equivalent to what? To R. Alright, so if we want to have a gain of 1, our feedback is simply going to be equal to R. Alright, but obviously we can play around with the feedback resistance to what? 2. So this whole lot, as long as grounded, it's like just 1 R. It's like our total value, our total for the R-to-2R, the Thevenin, the Thevenin resistance is just an R, just 1 R. Alright, so this is what we have. Ultimately, this is what we have. Yes, this here can what? Can be made better by the working out our. I mean, in practice, remember in practice that we're not even going to get accurate values. Why? Because here we don't use precise values here. This is 4,7 roughly. If you round off, this is 5 enough for us. All right, this is 5 enough for us. All right, so we're gonna say our 5-volt source there, okay, is basically being fed into our op-amp. So what do we mean here? What do we mean here is we mean that if we have a digital input here, these are switches. So the position of A, switch A, let's make this A rather than the source. Let's say the A where the switch is here. So if we close this, if we close all switches here, we've got the total supply. Well, almost. If we don't close this one and close the rest, it means we get what is the equivalent of what? Of 1101. But in voltages, it will be what? This is equivalent to our what? To our full load of 1111. All switches closed will give us that 4, so this is basically our equivalent of 15. All right, this is our loose equivalent of 15. Well, it's a technical. Sometimes we have to think out of the box. So we can remember even the other time I had to force specific values for it to give us what call this. I had to force in the previous scenario. I had to force our resistor values so that we could have a step of 1. But remember, I said the steps can be other than 1. They are not always 1. All right, they can be something else other than 1. So therefore, depending on your choices of values and your voltages, these circuits can get more accurate or whatever. But remember, because this is not a precise scenario anyway, your R value might not exactly be the same size as that. This is not a delicate situation like we have. We said one of the problems that we have with the weighted resistor was the precision of resistors, which makes it very expensive. So here, this is our equivalent of 15. So we have to divide this by what? By so if we look at, let's suppose we only had that one closed, that 2,5 is like our equivalent of 8. If we only had this one closed, that is like our 2. So you can roughly see that if we had this one closed here, this would be what? Did I say 2? 4. This here is the 2, that there is the 1. All right. So our step size is actually the what? The 0.3125 volts. In the other example that we had our step size being 1 volt. In this particular case, our step size is actually what? The equivalent of the unit load. All right. I'll call it the unit load because this is the voltage that the if I call it 8421, our unit, the 1, is represented by 0.3125 volts. So this will be our step. So it means that 2 volts has to be twice that. 3 volts has to be what? 3 times that. Okay, and obviously if this is twice that, 3 is 1, it will be that plus 2 times that, that is 3 times that. So you can see this is obviously, if this is 2 times this, and this is 2 times that, if C is 2 times D and B is 2 times C, therefore B is 4 times. So you see, if we have 1 there, 100 is 4. So our step size is actually 0.3125. I already say this is a nightmare, so now I know I'm sounding like I'm speaking a lot of gibberish, but try and go through it nice, much slower. Bring in your questions and we'll try to deal with them as we receive them. But I still gave you homework. Our homework, remember, was to look at what? Try and work out your V. Why it does look like an N? Your voltage at that point there. It helps you with your analysis. It's practice for analysis. But like I said I'll try to keep this short, and I'm talking forever. I think I have to just remind you, if you liked it, I know you didn't like this one. I know this was a nightmare, but I hope you liked it regardless, and then you can hit the like button, and then also you can subscribe again for not only working out, checking out your homework, but also if you drop another video, you will be the first to know. Till then, ciao ciao.